49 years ago, NASA launched a machine that was never supposed to outlive disco. It was built with less computing power than a modern calculator, powered by decaying plutonium, and given a 5-year expiration date. Nobody in 1977 believed it would still be transmitting in 2026. And yet, right now, more than 13 billion miles from where you are sitting, a signal is crawling back toward Earth from Voyager 2, carrying information about a region of space so strange that scientists still cannot fully explain what it's made of. This is not a story about aliens. This is something stranger because it's real. Voyager 2 has detected something at the true edge of our solar system that defies the models scientists built to predict it. Space out there isn't empty. It isn't quiet. It's dense, it's hot, and it's piling up like traffic jammed at a border checkpoint that shouldn't exist. And nobody, not NASA, not the physicists who've spent their careers on this data, knows exactly why. Before we get into what Voyager 2 actually found, you need to understand where it is, because the number alone is almost impossible to process. Voyager 2 launched on August 20th, 1977, 16 days before its twin, Voyager 1. Today, it sits over 13 billion miles from Earth, so far away that a radio signal traveling at the speed of light takes more than 19 hours just to reach it. Send a command, and you wait nearly 2 full days for a reply. That's not a delay. That's a conversation stretched across the solar system. Voyager 2 is the only spacecraft humanity has ever built that visited all 4 giant planets: Jupiter, Saturn, Uranus, and Neptune, a feat made possible by a planetary alignment that happens once every 176 years. NASA caught that window in the 1970s and never got another chance. After Neptune, in 1989, Voyager 2 kept going. It had nothing left to explore in the traditional sense, so it did something no one had planned for. It kept flying, straight toward the edge of everything we understand as home. On November 5th, 2018, Voyager 2 crossed the heliopause, the invisible boundary where the sun's solar wind finally loses its fight against the pressure of interstellar space. This was the moment Voyager 2 became only the second human-made object, after Voyager 1, to leave the sun's bubble of influence entirely. Scientists had a model for what this boundary should look like. They expected a gradual fade, a soft handoff between the solar wind and the space beyond it. That is not what Voyager 2 found. The instant it crossed the heliopause, its plasma instruments recorded something almost violent by cosmic standards. The density of charged particles around the spacecraft jumped by a factor of roughly 20, almost instantly. One moment, Voyager 2 was moving through thin, hot plasma blown out by our own sun. The next, it was surrounded by plasma that was colder and dramatically denser than anything inside the solar system's bubble. It was as if the spacecraft had punched through an invisible wall into a completely different ocean. Here's where it gets stranger. Voyager 1 had already crossed this same boundary back in 2012, 6 years earlier, on the opposite side of the solar system. If the heliosphere were a simple, symmetrical bubble, you'd expect both probes to report roughly similar conditions when they crossed. Instead, scientists at the Johns Hopkins Applied Physics Laboratory, reviewing data from both spacecraft, found something that genuinely puzzled them. The 2 probes crossed the heliopause at nearly the same distance from the sun, despite one crossing during a period of high solar activity and the other during a period of low activity. But the physics scientists understood at the time that shouldn't have happened. The boundary should have shifted with the sun's mood. It didn't. Then came the part that turned a boundary crossing into an open scientific mystery. After Voyager 2 settled into interstellar space, its instruments kept measuring the density of the plasma around it, and that density didn't stay constant. It didn't level off the way researchers expected. Instead, over time, it kept climbing. Data compiled by scientists studying both Voyager spacecraft showed that the density of the material just outside our solar system's edge was continuing to increase well beyond what any existing model had predicted. And researchers openly admitted they did not know where the increase would stop or why it was happening at all. Some scientists have proposed that interstellar material is essentially piling up right at our solar system's doorstep, compressed like snow in front of a slow-moving snowplow, as our sun pushes through the surrounding cloud of interstellar gas. Others point to something even stranger: magnetic field lines from interstellar space draping over the heliopause, possibly strong enough to trigger plasma instabilities. Nobody expected to find this close to home. Both explanations are still on the table. Neither has been confirmed. And the only 2 instruments in existence capable of measuring it directly are 2 aging spacecraft that were never built for this job in the first place. So here is where we stand right now in 2026. Voyager 2 is still out there, still transmitting, still measuring a boundary layer of space that behaves nothing like the textbooks predicted. And as you're about to see, the mystery doesn't stop at density. What Voyager 2 measured about the temperature, the magnetic field, and the sheer unpredictability of this region is even harder to explain. And it's forcing scientists to rethink what the edge of the solar system actually means. If you want to understand exactly what NASA found next, and why engineers are now racing against time before Voyager 2 goes silent for good, stay with me because it only gets more unbelievable from here. Let's talk about the temperature, because this is where Voyager 2's data stopped just being unusual and started being genuinely hard to explain. When scientists first modeled the region beyond our solar system, they expected interstellar plasma to be cold, not freezing in the way we experience cold, but cold by plasma physics standards. Calm, low energy, unremarkable. Voyager 2's instruments told a different story. The plasma, just beyond the heliopause, came back hotter than the models predicted, and not by a small margin. Researchers publishing in Nature Astronomy described the very local interstellar medium around Voyager 2 as variable and hotter than expected, sitting right at the boundary layer the spacecraft had just crossed. Now pair that with the magnetic field. Before Voyager 2 crossed the heliopause, physicists had a rough idea of how strong the interstellar magnetic field should be based on theoretical models and indirect observations. When Voyager 2 actually measured it directly, becoming only the second spacecraft in history to do so, the field came back stronger than expected. That single data point mattered more than it sounds like it should, because a stronger magnetic field changes how the boundary of our entire solar system interacts with the galaxy around it. It suggested that the sun's protective bubble isn't sitting in some quiet, empty pocket of space. It's being pressed on, squeezed, shaped by forces that are more powerful than anyone had calculated. Here's the part that should genuinely unsettle you. Some scientists now believe those magnetic field lines don't just sit outside our solar system passively. They think interstellar magnetic field lines are draping directly over the heliopause, the same boundary Voyager 2 crossed, and that this draping effect could be strong enough to trigger something called an electromagnetic ion cyclotron instability. In plain language, the interaction between our sun's bubble and the magnetic field of the galaxy may be violent enough, right at that boundary, to strip plasma away from the region entirely. That's not a gentle handoff between inside and outside the solar system. That's an active, ongoing tug of war happening 13 billion miles from where you're reading this, and Voyager 2 flew straight through the middle of it. And then there's the density problem again. Except now it's not just a mystery, it's an unfinished one. Newer modeling work published in 2025, drawing on years of combined data from both Voyager spacecraft, describes the region the probes are now traveling through as the outer heliosphere, a zone where interstellar plasma flow is significantly slowed and heated by compression against our solar system's bubble. According to that research, both probes are still relatively close to the heliosphere in interstellar terms, and they may be approaching a maximum in plasma and neutral atom density somewhere between 200 and 250 astronomical units from the Sun. Voyager 2 right now sits at roughly 143 astronomical units. Voyager 1 is further out, at around 172. In other words, according to current models, the density and pressure Voyager 2 has already reported may not have peaked yet. Whatever is compressing and heating the space at the edge of our solar system could still be building. Nobody knows what it will look like when it does. While all of this was happening scientifically, Voyager 2 was also fighting to survive. And this part of the story is real, documented, and terrifying in its own quiet way. On January 25th, 2020, Voyager 2 failed to execute a scheduled maneuver correctly. Two power-hungry systems ended up running simultaneously, tripping the spacecraft's onboard fault protection. Automatically, without any human involved, Voyager 2 shut down its own science instruments to protect itself, going dark on the very measurements scientists depend on. For more than a month, engineers at NASA worked to bring it back online. It wasn't until March 2020 that Voyager 2 fully resumed normal science. Operations. A 43-year-old spacecraft alone, over 11 billion miles from anyone who could physically help it, diagnosed and protected itself using code written in the 1970s. Then came 2023. In August that year, a scheduled command accidentally tilted Voyager 2's antenna just 2 degrees away from Earth. 2 degrees, that's all it took to sever contact with a spacecraft that far away. For 37 agonizing hours, NASA had no confirmed communication with Voyager 2 at all. Engineers didn't know if the spacecraft would ever hear them again. In the end, the Deep Space Network's most powerful transmitter, located in Canberra, Australia, sent what NASA internally called an interstellar shout, a signal powerful enough to reset Voyager 2's antenna orientation across billions of miles of empty space. It worked. Contact was restored. But for well over a day, humanity's most distant living machine was effectively lost, drifting through the exact same dense, hot, magnetically hostile region of space we've just described, with no way to tell us what it was seeing. That near loss is exactly why NASA has spent the last 2 years making one of the hardest decisions in the mission's history, deliberately shutting Voyager 2 down, piece by piece, on purpose. In September 2024, engineers powered off Voyager 2's plasma science instrument, the very instrument that had confirmed its crossing into interstellar space back in 2018. In March 2025, its low-energy, charged particle instrument went dark too. Its cosmic ray subsystem is scheduled to be switched off later this year, in 2026. Each shutdown isn't a failure, it's a calculated trade, sacrificing one set of eyes to keep the spacecraft's heart beating a little longer. NASA's own Voyager project scientist, Linda Spilker, put it in stark terms that stuck with me while researching this. Every day really could be the last. So Voyager 2 is racing the clock in 2 directions at once. It's still transmitting data about a boundary of space more turbulent and unpredictable than anyone modeled. And at the same time, it is being slowly, deliberately powered down, instrument by instrument, in a desperate effort to keep it alive into the 2030s. What happens when the density Voyager 2 has been tracking finally reaches its predicted peak? And what happens if it does so after NASA has already been forced to switch off the very instrument measuring it? That's exactly where this story goes next. Here's a question that sounds simple but isn't. What actually happens when Voyager 2 finally goes silent? Not in some vague, distant sense, but literally. Engineers at NASA have already run these numbers, and the answer is closer than most people realize. Voyager 2 is powered by 3 radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium-238 into electricity. That plutonium has been decaying since before the spacecraft even launched in 1977, and it never stops. There's no refueling, no swapping batteries, no repair mission possible at 13 billion miles. Every single year, without exception, Voyager 2 loses about 4 watts of power. 4 watts doesn't sound like much until you remember the entire spacecraft currently runs on roughly the same power draw as a couple of household light bulbs. Losing 4 watts a year, on a budget that small, is not a minor inconvenience. It's a countdown. That countdown is exactly why NASA has spent the last several years making a series of decisions that would have sounded unthinkable to the original 1977 mission team, switching off instruments on a spacecraft that took nearly 5 decades to reach where it is, one by one, in order, on purpose. The Voyager science and engineering teams didn't make these calls in a panic. Years ago, they sat down and mapped out in advance the exact sequence in which each instrument would go dark, prioritizing whichever ones still had the most scientific value against how much power they consumed. Voyager 2's plasma science instrument, the one that confirmed its 2018 crossing into interstellar space, was switched off in September 2024. Its low-energy charged particle instrument followed in March 2025. Its cosmic ray subsystem is scheduled for shutdown sometime in 2026. By the time that happens, of the 10 identical sets of instruments Voyager 2 originally launched with, the majority will have gone permanently dark. What's left after that is almost poetic in how minimal it becomes. NASA's current plan is for both Voyager spacecraft to eventually operate with just a single working science instrument each, likely the magnetometer, stretching that final trickle of data into the 2030s if nothing unexpected goes wrong first. And NASA has been unusually blunt about the odds of that. These are spacecraft that have now weathered nearly 50 years in the most hostile environment humans have ever sent anything into, cooked by cosmic radiation, chilled to temperatures near absolute zero, running on code and memory chips that predate the personal computer. Every additional year is, by any reasonable engineering standard, borrowed time. And here's the part that makes this more than just a story about hardware dying slowly. Voyager 2 isn't only measuring plasma density and magnetic fields out there, it's carrying something else, something that has nothing to do with science instruments at all. Bolted. To the side of the spacecraft is the Golden Record, a 12-inch gold-plated copper disc containing greetings in 55 languages, natural sounds from Earth like wind, rain, and animal calls, and 90 minutes of music spanning cultures and centuries. It was assembled by a team led by astronomer Carl Sagan in 1977, not because anyone expected it to be found, but because sending it mattered on its own terms. Long after Voyager 2's last instrument goes dark, long after NASA loses the ability to hear anything back from it at all, that record keeps traveling. It doesn't need power. It doesn't need a working transmitter. It will simply keep moving, carrying a physical snapshot of who we were in 1977, drifting through a region of space we still don't fully understand, for what scientists estimate could be billions of years. Think about what that actually means. The same spacecraft that detected an unexplained density spike at the true edge of the solar system, and the same spacecraft that measured a magnetic field stronger than any model predicted, the same spacecraft that nearly went dark forever in 2023 after a 2-degree antenna error, is also carrying humanity's introduction to whoever or whatever might one day find it. It is simultaneously a scientific instrument still generating new questions in a time capsule that will outlive every human currently alive, every government currently in power, and quite possibly every trace of civilization we'd recognize today. There's a sobering estimate that puts this in perspective. Based on current trajectory calculations, Voyager 2 is heading in the general direction of the star Ross 248, though it won't make anything resembling a close approach. Even at the almost incomprehensible relative speeds involved, scientists estimate Voyager 2 wouldn't come within a meaningful distance of another star system for roughly 40,000 years. That's not a typo. 40,000 years. For context, that's roughly 8 times longer than the entire span of recorded human history. Voyager 2 will likely be silent, unresponsive, and completely alone for the overwhelming majority of that journey, a dead machine drifting through the exact dense, turbulent boundary layer we've spent the last 2 sections describing, carrying a message from a civilization that may look nothing like whatever or whoever eventually crosses its path. So where does that leave us right now in 2026? We have a spacecraft that is actively dying by design, deliberately starved of power to buy a few more years of data. We have a genuine, unresolved scientific mystery about why the space just outside our solar system keeps getting denser and hotter than predicted, with researchers openly admitting they don't know where it stops. And we have a handful of years left realistically before Voyager 2's last instrument goes dark for good, and this unprecedented, decades-long conversation between Earth and the edge of the solar system finally goes silent. What happens in that final window matters more than most people realize, and there's one more piece of this story that ties everything together. From the density spike Voyager 2 first detected back in 2018 to the very real countdown NASA is racing against today. So let's bring this all the way back to the beginning, because everything Voyager 2 has found out there connects into one uncomfortable truth. We built a map of our solar system's edge based on theory, and reality didn't agree with it. Go back to what scientists actually expected before 2018. The heliopause was supposed to be a soft transition, a gradual fade from the sun's influence into the quiet dark of interstellar space. Instead, Voyager 2 punched through a boundary where plasma density jumped by a factor of roughly 20 almost instantly, where temperatures came back hotter than predicted, and where the magnetic field turned out stronger than any existing model accounted for. And rather than settling into a stable, predictable interstellar environment afterward, the density kept climbing, with researchers openly stating they don't know when or where it will level off. That's not a footnote in an astronomy journal. That's an active, unresolved mystery happening right now at the true edge of everything we call home. And the reason we know any of this at all comes down to an almost absurd stroke of engineering luck. Voyager 1's plasma instrument had already failed by the time it crossed the heliopause back in 2012, which meant scientists had to infer that crossing indirectly through other instruments. Voyager 2's plasma instrument, remarkably, was still working when it crossed in 2018, giving researchers the first direct, real-time measurements of what this transition actually looks like. That instrument functioned for 6 more years after that crossing, before NASA had to shut it down in September 2024, not because it broke, but because the spacecraft simply couldn't spare the power to keep it running any longer. Every single data point in the last 2 sections of this story exists because a probe built during the Ford administration happened to still be working exactly when it needed to. That's the part of this story that should stay with you. This isn't a mystery humanity solved. It's a mystery humanity barely caught in time, using a machine that was never designed to still be operating, sending back measurements from a region of space nobody expected. To be this active, this dense, or this poorly understood. NASA's own scientists have said plainly that they don't have a confirmed explanation for why the density beyond the heliopause keeps rising. Competing theories point to interstellar material piling up against our solar system, like traffic backed up at a border crossing, or to magnetic field lines draping over the heliopause and triggering plasma instabilities right at that boundary. Both remain open. Neither has been ruled in or out. And the only tools capable of settling that question are 2 aging, dying spacecraft with a shrinking number of years left to answer it. Here's what makes 2026 specifically matter. This is the year NASA is scheduled to switch off Voyager 2's cosmic ray subsystem, following the same sequence that already claimed its plasma science instrument in 2024 and its low-energy charged particle instrument in 2025. Each shutdown narrows the window for catching whatever comes next in that density curve. If the interstellar medium around Voyager 2 truly is building toward a peak somewhere between 200 and 250 astronomical units, as recent modeling suggests, the spacecraft may or may not still have a working instrument capable of registering it when that peak actually arrives. We are, quite literally, in a race between a scientific mystery and a countdown clock built from decaying plutonium. And underneath all of it, there's still that record. Whatever happens to Voyager 2's instruments, however many more years of data NASA manages to pull from it, the golden record keeps traveling regardless. It doesn't need power, and it doesn't need anyone back on Earth to still be listening. Somewhere in the next 40,000 years, long after every question raised by this video has either been answered or forgotten, that disk will still be out there, carrying greetings in 55 languages and the sound of Earth's rain and wind and whale songs, moving through a region of space that, even now, we don't fully understand. That's what makes Voyager 2's story different from almost anything else humanity has ever built. It's not a monument. It's not finished. It is, right now in 2026, still actively working, still confusing scientists, still redefining what the edge of our solar system actually looks like, while simultaneously being deliberately powered down piece by piece to buy a few more years of answers. Somewhere between those two realities, the discovery and the countdown, is the actual story of what's happening 13 billion miles from where you're sitting. So here's the real question this leaves us with. Voyager 2 has already shown us that the edge of our solar system is denser, hotter, and more turbulent than any model predicted, and researchers still don't know why. NASA is now racing to keep at least one instrument alive long enough to find out. Do you think we'll get a real answer before Voyager 2's last instrument finally goes dark? Or is this a mystery that gets left permanently unsolved, sealed inside data from a spacecraft that will eventually go silent for good? Let me know what you think in the comments below. And if this kind of deep, fact-checked look into what's actually happening at the edge of our solar system is something you want more of, make sure you're subscribed, because Voyager 2's countdown is still running, and there's a real chance we get another update on this before the decade is out.